Hello and welcome to Team 22's senior project, the Woodward Incorporated Vacuum Oven. The members of this team are Drew Sigiersma, Seth Gibson, Dylan Howcroft, Michael Whittle, and Jordan Cooper. Now the purpose of this project is that Woodward Incorporated is in need of a vacuum oven in their manufacturing process. The oven that they currently use to dry acidic compounds off of nickel alloy parts is nearing end of life, and they wish to replace it with a vacuum oven that is able to fit the same parts. This new system was to be designed with respect to efficiency, reliability, and durability, i.e., not only should this new oven decrease the current operational cycle time, but it should also be easy to use and be operational for a long period of time. The top-level operation of this new oven was designed with this in mind. The oven is to run its cycles in one of two modes, with and without a vacuum pump pulling the atmosphere inside the oven down to 1 torr. The entire system must have an emergency kill switch and will be operated using an HMI device loaded with a clear and intuitive operational program. Above all, the oven must heat the enclosure to the target temperature within a reasonable amount of time, and all factors must be monitored by the system. The specifications provided to us by Woodward are given to us here in more detail. The inside dimensions of the oven will be equal or greater than 18 by 18 by 27 inches. The dimensions of the opening of the oven will be at least 90% of the interior dimensions. The oven enclosure and the ancillary components will all be able to fit on the provided table. The oven will be made out of SAE 304 or SAE 316 stainless steel. The oven will be able to preheat to 250 degrees Fahrenheit in at least 30 minutes. It will be able to reach a maximum temperature of 300 degrees Fahrenheit. It will be able to reach a maximum vacuum of 1 torr above absolute pressure. And it will be able to operate off of a 120 volt input. The system is divided into 5 major components: the oven enclosure, the vacuum pump it's attached to, the heating element inside the enclosure, and the control box holding the PLC and the HMI. Standard operation of this system is pretty straightforward. The operator turns on the system and starts to preheat the oven. They set the target values, including temperature, pressure, bake time, and when the preheat temperature has been reached, they load the parts inside the oven and start the cycle. When a cycle starts, it reaches the set targets, i.e. the target temperature and pressure, or just the temperature if it's running a normal oven cycle. Once these are reached, the bake timer starts, maintaining these values until the time elapses. Once it ends, the indicator light comes on, the oven will safely repressurize, and the dry parts can be unloaded. To heat this enclosure, we use conductive heating, which is the best medium for heat transfer in a vacuum, at least in this scenario. The inner vacuum chamber is built to be airtight, based on pressure specifications. The outer chamber was built not only to hold heating insulation, but was also built to have a simple aesthetic to avoid distraction. Under the 120 volt input limitation the electrical components are placed under, the outputs will be controlled by 24 volt coil operated relays. A 15-pin D-type connection will be used for the PLC to operate the pump, and the solenoids and sensors exposed to the atmosphere inside the oven will be resistant to corrosive, high temperature, low pressure environments. On a higher level, we approached this design in a way that allowed us to create a system of equal or greater quality and efficiency of the oven we're replacing. Woodward experimented with using vacuum ovens in the past and preferred their use over standard ovens. The material used for the majority of the oven system was 304 stainless steel, due to its resistance to Okai 33's corrosiveness, along with its excellent heat retention and conductivity. And there we have the early CAD model of the oven enclosure in its entirety, fit with a hinge door, a locking mechanism, and a valve stack attached to the back, managing and monitoring the intended vacuum and repressurization after a completed cycle. Here we have an exploded view of the oven system, including the outer and inner portions of the oven, the heating plate, and the door. While testing this heating pad design, we found that the heating element was not able to make full contact with all 3 plates due to extensive warping. We've switched to a design with a single plate with 2 heating pads attached to the underside for the best heat transfer with the least amount of warping. More on this later. The components used in and around the oven enclosure were included in our design for ease of assembly and serviceability, thereby extending service life of the system. These components include the sensors, the heating element, and the wiring. The insulation between the inner and outer layers can easily be replaced via drilling out and replacing rivets. Finally, the stainless steel components used in the enclosure were primarily laser cut, bent, and welded at Woodward's preferred machine shop. The enclosure was vigorously tested and validated using hand calculations for pressure dynamics and heat transfer of the enclosure interior. These calculations were compared to simulated models undergoing similar pressure and temperature tests. The simulated internal structure is shown here to be able to withstand the vacuum with a factor of safety of 6.66. The stress and deformation during this vacuum are within acceptable ranges of stress, and differences between the simulated and hand-calculated results are acceptable as well. We can also calculate here that the insulation is able to diffuse the majority of the heat from reaching the outer enclosure. Continuing our discussions of our design choices, the vacuum pump selected for this system was the Edwards NXDS-6i. A pump Woodward already had on hand and could easily restock and repair that could pump down to the specified vacuum within a reasonable amount of time. The vacuum pump will be connected to the oven valve stack using these components to ensure a vacuum sealed connection. And to validate if this pump works to our needs, we calculated the pump down rate needed to reach 1 torr within 30 minutes, which comes down to 0.000528 cubic meters per second, or 1.9 cubic meters per hour. This is approximately 1/3 the evacuation rate of the pump. This gives us a more than ample pump down rate with room to breathe if we run into any issues. The heating element selected was a 720 watt silicon heating pad, a conductive heat transfer element that's able to heat the interior to the specified temperatures in this harsh environment within the specified time frame. For the most effective heating, 2 of these elements will be attached to the underside of the shelf using heat-resistant adhesive, allowing for the best possible conductive heating into the parts in the vacuum. While we were not able to validate that this system could dry OKite 33 completely, we were able to determine that just one of these heating elements could reach the heating capacity needed to evaporate the corrosive material, especially in a vacuum. More specifically, using FEA simulations, we were able to determine that the system reaches 250 degrees in 10 minutes and 300 degrees in 13 minutes, both without a vacuum. The PLC controlling the system is an Allen Bradley 1769 L18ER B1BB, which was selected due to its compatibility with existing Woodward programming systems on top of having the right amount of inputs and outputs for all parts of the system. The PLC would monitor and control all the inputs and outputs displayed here. We'll use a magnetic read switch to monitor the status of the door. Separate input signals will notify the PLC if the E-stop has been pressed and if the safety relay is off. This will ensure the cycle is not restarted immediately once the E-stop has been reset, but only after both the E-stop and the safety relay are reset. A 0 to 10 volt pressure signal will be routed to the PLC via the analog expansion slot. A high-heat stainless steel pressure transmitter was selected to withstand the maximum temperature and the corrosive fumes of the OKite 33. Temperature sensing will be performed by a thermocouple surface mounting to our heating pad. This will ensure accurate measurement when a vacuum heating is required. The thermocouple signal is processed by a signal converter module with a 0 to 10 volt analog output, suitable for the expansion slot. Finally, the PanelView Plus 7 HMI was selected as the simplest, most straightforward method of operator interaction with the system logic and presenting the info gathered from our sensors. Here's a quick look at the programs being loaded into the HMI that will be used to communicate with the PLC. As you can see, we're trying to make all information be presented as clearly as possible, and all avenues of operating this system are intuitive to use by any operator. Currently, our testing programs are able to communicate with the PLC, allowing us to control the important system functions, which we're working to tie into these intuitive menus in further iterations. Here is our completed assembly at this current time. We're continuing to make the system as airtight as we can, in all senses of the word, ensuring that the heating, vacuum, and automated systems are up and running, testing the full functionality as we go, and making the right moves when tests aren't reaching satisfactory results. Thank you, and have a nice day.